Hi there, and welcome to this breakout session on SolidWorks Flow Simulation, where we're going to be taking a look at how we can use the flow simulation tools that are adapted for SolidWorks to analyse our designs and improve them before we go ahead and have things made. So what we're going to do is have a look at the two primary uses of SolidWorks Flow Simulation. There are others, but primarily I see SolidWorks users using flow simulation to analyse electronics cooling enclosures. So these are situations where we've got a number of electronics components. We may have fans, we may not, we may be just passively cooling our system using heat sinks, but we've got a study that we're going to have a look at which is going to be based around that sort of situation. Or alternatively, I do see a lot of other users analysing valves and pipe flows with SolidWorks Flow Simulation. Okay, so what we've got here first of all is our enclosure. So in here you see we've got a number of components. I have blown them up a bit just to make sure it's clear and we can see everything that's going on here. So we've got our transformer in here, we've got a number of coils, we've got some capacitors, we've got a heatsink in here, we've got an op amp in here, etc, etc. We've got a number of components in there which are going to be producing heat. We've also got a fan out here, so here we can see we've got our cooling fan here, and finally you'll see we've got our outlet vents each here, so we've got a number of slots and a large number of holes there which we're actually going to modify and take advantage of some other tools to analyze. Okay, first of all I'm going to switch over to my analysis configuration and hopefully you'll notice a number of changes. The lid does still exist, I've just hidden it so that we can see it a bit better. But first big thing you hopefully notice is that all of those holes have gone and we've replaced them with a massive hole, and this yellow component here is just a lid. So when I say a lid, it's just a solid body which has been used to plug that gap. We're going to apply properties to that gap or to that solid body or lid in a moment. We've done something similar over here to account for the fan, and we've also got some lids on these slots. You just can't see them, or for some reason I haven't made them yellow. Alright, so let's go ahead and start defining our study now. So the first thing we need to do is generate a new study. So I'm going to come up to my wizard, and this is SolidWorks' way of guiding you through the setup process. So here we can set up a new project, so let's call this flow cooling. We're going to base that on the current study, current configuration, sorry, and hit next. Here we can set up our units. I'm pretty happy with most of them. I'm just going to change my temperature units to degrees C, just so it's a bit more representative of things that we see every day. And then we'll go through to next. Now here we can specify what type of analysis we want to conduct. So in this case it's going to be an internal study. We've got an external enclosure around our volume of air, and we're going to analyse what's going on inside. SolidWorks by all means has the capability to do an external study. We've got something similar, or something representative, sorry, here. So we've just got flow around the outside of a cylinder, and so SolidWorks does have the capability to do that also. Both these cases that we're looking at in this case are internal. And we've got a number of other options here as well. So we've got the opportunity to exclude cavities without flow conditions. So I'm going to keep that checked. And that's just so in case we've got any internal volumes inside any of our components here, and we're not interested in analysing what air inside there is doing, so we can ask SolidWorks to ignore them because they haven't got flow conditions. We can also check any one of these boxes to include any particular physical phenomena. So we've got heat conduction in solids, which is something we're going to tick. So this is going to allow SolidWorks to not only conduct a fluid analysis and analyse where the fluid is going, so what the air is doing, we can also analyse the thermal distribution throughout our solids, so throughout all of our components as well. We can include radiation. That's really only an issue if we've got high levels of radiation from really hot heat sources, etc. So I'm not going to include that this time. We've got the opportunity to conduct a time-dependent study. So this is a transient analysis. So say, for example, if we're expecting flow conditions to vary with respect to time, or we want to change our boundary conditions with respect to time, we can do that using a time-dependent study. We can also include gravity, which, well, is what it says, and rotation is an option that allows us to include rotating coordinate reference systems for the inclusion of things like fans. Okay, next we just need to specify our default fluid. This is very simple in this case, but you'll see we've got a number of other default materials, much like the standard SolidWorks materials library. And we'll come back to the engineering database shortly, but we'll have a look in here. We've got air, so I'll just double click that, and that's going to add that into our study as the default fluid. Okay, hitting next. Now SolidWorks is just going to ask for our default solid. So in this case, I'm just going to grab an aluminium. Let's go for an aluminium 6061 alloy. So this is essentially what SolidWorks is going to make every solid component out of, unless we specify otherwise. So this is the default setting. So I'll hit next, and we can specify roughness values if we want. I'm going to leave those at 0 for the time being, and I'm going to assume that the outer wall, so the external wall of our control volume, is an adiabatic wall, so there's no heat transfer through there. Okay, finally we can set up our ambient conditions. So this is where, if you were conducting an external study, we would input our flow velocity. So if we had air flowing past it, we could do that just in here. For the time being, I'm going to leave everything at default. I'm going to assume that the initial solid temperature is 20.05 degrees, and I'm also going to assume that the ambient air temperature is something similar. So we'll hit next. Finally, we specify what we want to do with our mesh. For those of you that saw my FEA breakout session, you'll know that hopefully that the mesh is very important and dictates to a high level what your accuracy is going to be. So in this case, I'm just going to leave that at the defaults, but we've got a way of controlling the mesh here, which is very simple and transparent to the user just by way of a slider. We can specify the size of particular features that we've got in our geometry, or later on you'll see we can apply further controls to modify the mesh slightly. Okay, so what we're looking to do here is make sure that our heatsink, so that's this guy over here, is coming in at below 59 degrees C, and our op amp, that's this guy here, is coming in at somewhere below 51.6 degrees C. So these are our expectations, so that's what's going to dictate whether our design is successful or not. So first thing we need to do is go ahead and start specifying the materials for our components in here. And that's very simple. If I right click on my solid materials and go to insert solid material, all I need to do is select specific components. So for example, I'm just going to grab the PCB board here. You should be able to see that highlighting just here. You can't see most of it because I've got a decal over there with just a simple PCB graphic on there. But what we can do is grab some of the predefined tools, and inside my laminates I've got an FR4, which is a typical PCB material, and I just hit OK, and you'll see SolidWorks will add that item to the tree, and now everything else will be assumed to be that aluminium 6061 alloy, except our board, which is going to come in at that FR4 plastic. I'm going to do something similar to my heatsink, so let's go ahead and do that. Now let's grab just a standard aluminium, so it's not an alloy, it's just a straightforward aluminium, and you'll see it's very simple like that. There are obviously numerous components in there that will require a definition of the materials. What I will do, if I switch over to my complete study, I will show you one very neat thing that we can do, and that's so you see we've got all of our materials set up in here. So let's just grab one of these. I'm just going to copy that over, so I'm going to ask SolidWorks to stick it in my flow cooling study. Hit OK, and now you'll see when we switch back to our flow cooling, you'll notice that SolidWorks has added that transformer material in there for us. So we can go ahead and do that for all of them if we wish. So we can port the inputs that we've put on our studies back and forth between individual studies as and when we please, which is a really nice addition that SolidWorks have given us. Okay, the next important thing is setting up our boundary conditions. So what we're going to do is right click on the boundary conditions and insert some, and it's a very simple case of grabbing the internal faces of our lids. So I'm just going to whip through and grab these 9 faces, and these are going to be my outlet conditions. So I'm going to specify just a basic temperature outlet. We're going to leave that at an environmental pressure and hit OK. So that's just ambient pressure out there. Next, we need to go ahead and define our fan. So this is a perfect time for me to go into our engineering database and have a look at what we've got in here. So this is very similar to the standard SolidWorks database, but this is the one that's attached to Flow Simulation, and it's got a number of additional characteristics in here that we can grab. So for example, we've already seen the materials. We've seen our solids, so this is where I grabbed that FR4, which was under my laminates. That's the FR4 there. We can also take advantage of many other gases, liquids, and non-Newtonian liquids. we can use, for example, models for PCBs. So in here, you'll see that I've got a PCB which is laid up with thicknesses of either conductive layer or insulative layer in here. So we can specify full characteristics for a printed circuit board in there. And we can go through and you'll see we've got a vast array of available materials or models that we can stick in. In this case, we're going to have a look at the fans, and you'll see that under our fans, we've got another vast catalogue of potential fan characteristics that we can use. So let me just jump out of there. Right click on my fans and insert one. And I'm going to grab this face oh, that's not the face I'm after. I'm just going to grab this face here and specify my fan. So I'm going to come into my fan curves, grab that Pabst one, going to go into the DC axial ones, probably my 400s. Let's grab that 405. I've done well to remember that, and add that in just like so. So that's going to take the fan curve, so all the information from the manufacturer. And SolidWorks have been in contact with a large number of manufacturers who have given us their info, because obviously it's great for them, because people can then model their fans in their geometry and say, yes, this is the one I want to use it, and then go ahead and buy that from the manufacturer. So the manufacturers are always updating this information, which is great for us because it's a very quick and easy way of including those sorts of features within our designs. Okay, next we need to go ahead and specify our thermal loads now. So this is where we're going to be putting our heat sources in, signified by the heat sources icon. So I'm just going to come in, grab that volume heat source, and I'm going to grab, first of all, these blue components here. So I've handily named these, so I've just put some text on the top of each of these. So I'm going to specify a temperature in this case, and those are going to be 45 degrees C in there. Okay, so that's our first lot. Our second lot, in this case, we're going to grab the other four and put in our 35 degrees C. We've also got these large components over here, which, as you can see, aren't specified by temperature. They are instead a power heat input. So I'm going to grab those components there and instead use the heat generation rate option to specify 2 watts for each of those. Like so. Very quick, very simple. Again, very much like the FEA analysis tools, we can just pick off our geometry and apply each of our individual settings to each of our individual components with great ease, because it's already there and on our screen and ready to go. So I'm just going to stick 0.5 watts on there, etc, etc. I don't need to go around and do everything. We'll see that later on. Okay, finally, I'm just going to grab my perforated plates, which is something that allows me to, as you will see, cut out really complex holes in the walls. So this is geometry that would take a long time to mesh because we need small elements to resolve each of the individual holes that we had on there. Instead, what we can do is grab our perforated plates, specify where we want to apply that perforated plate, and then add our own material. So in this case, I'm just going to stick in a new one. So let's go with, just call it my perf plate, something simple so I can pick it out. And so here we can see, you will see that we can specify a number of hole regimes and how we want to specify that perforated plate. So in this case, the hole diameter, we've got 0.002 meters. And I'm going to specify it using a checkerboard in this case. So the checkerboard distance is just the distance between the two centers. So we're assuming that it's in a checkerboard pattern. So I'm just going to stick 0.004 in there. You'll see SolidWorks will work out that free area ratio. So that's the ratio of airspace, so the gaps essentially in the material, to solid material. We'll hit save. And then we can come through and have a look at our user defined. You'll see that my perf plate has just come through there. We can hit OK. Now SolidWorks is going to assume the numerical characteristics of that wall without actually having to model it and put in all of the mesh controls to mesh it accurately. Finally, all we're going to do is set up some goals. So our goals are the way in which we can control the solver. So SolidWorks works exactly the same as any other CFD package in that it's a perpetual solve. There is no finite answer to the equations. Instead, we are modeling and conducting almost like a numerical analysis to achieve our results. And so unless we stop it manually or tell SolidWorks when we want it to stop, it will continue to solve infinitely. It will continue until the computer dies. So what we need to do is control or give SolidWorks a way to control or decide when to stop. So what we use is what's referred to as goals, and essentially SolidWorks will dictate the values of them. So say, for example, I'm going to grab the solid temperature here of, so the max solid temperature of my heatsink. And so SolidWorks will have a look at the maximum temperature of that heatsink now. And once the value that it's got starts fluctuating within a specified bracket, so the fluctuations are small enough, then SolidWorks will say, well, I think that value has converged. So we can say, well, I want you to wait until each of these individual values has converged, and then SolidWorks, once it's reached that point, will say, yes, I think I'm done, and stop solving. Okay, so I'm going to grab that, and I'm also going to grab my op amp just there, hit OK, and that's our setup and ready to go. So next, all we would need to do is go ahead and click Run. And you'll see a really nice thing SolidWorks have given us the capability to do is specify how many CPUs to use, so we can use all of the available ones. Or, for example, if you want to carry on word processing or something like that, we can specify 3, and then we'll have a leftover CPU which will enable us to do other tasks at the same time. We can also push that solve out to a different machine if we've got any networked computers set up for it, and we can use batch results, so we can analyze if we had more than one study. So in this case we had 3, we can analyze more than one at a time. Alright, now let's switch over to my completed study now, and we're going to have a look at some results. So let's just collapse that tree and expand my results tree, and now you'll see at the moment it's all greyed out, and that's because we haven't got any results loaded in. Now, this is another really nice feature, so we can make changes between studies, run studies based on the same setup, but have different result sets. So now we can choose which result set to load in. So for example, I've got 2 available ones in here, so I've got 1 and 2. So I'm just going to select number 2 and load in my results from the second study that I generated. Okay, and now you'll see that we've got all of the features that we have in that tree now active and colourful and available for us to select. So first of all, what we're going to do is have a look at this cut plot here, and this plot's showing us our mesh. So if I just hide my geometry for a second, we can come in and have a look at the mesh that we had on there just to analyze our study. So we can grab that cut plot and just drag that through anywhere we like so, and have a nice look at each of the key locations. So for example, around our heatsink, and we can have a look at how fine our mesh was in there. And we can drag that through as much as we like, or alternatively we can have a look at a 3D view. So let's have a look at our partial cells in this case. So these are just cells that have both fluid and solid within them. And you'll see that we can get a rough idea of how fine that is, and from a top view we can see where it is finer around each of our individual components. But you'll also notice that because we have got so many cells in there, that does get quite convoluted, and sometimes it is easier just to drag that cut plot back and forth through our geometry and have a look at just what's going on at each individual location. Okay, the cut plots, actually let's bring the geometry back and we'll hide that lid again. The cut plots also allow us to have a look at the temperature and things like that, so any of the fluid characteristics that we might be interested in. Let's switch that plane to our right plane, much like the mesh one that we had before. And so in this case I'm going to use a contour plot and have a look at the temperature of the fluid. So if I hit OK, you see SolidWorks gives us that cut plot, and again we can drag that through and have a look at what temperature the fluid is around these areas. So here we can see we've got our high fluid temperature regions in and around this heatsink, and these are coming in at about 72 degrees, you see there. And so we can drag that through our geometry and analyze how the fluid temperature is varied throughout the entire computational domain. So let's hide that. That's one of our results analysis tools. Very much like the FEA tools, we've got a number of tools which give us visual representations of the results. We've also got a couple of tools which give us much more numerical information. We can plot next our surface results. So for example, I may want to grab a number of surfaces from my south bridge. Let's perhaps grab the top face and a side face of my op amp, like so. And let's just have a look at a top and a side of my heatsink as well. And in this case, I'm not going to have a look at the fluid temperature, I'm going to have a look at the solid temperature. So let's hit OK on there. And now you'll see SolidWorks has painted these with the temperature that we've got on there. So we've got a lot of red regions. We've also got some green regions in here, which is slightly lower temperatures than those really hot regions. So we've got a slightly cooler region down the bottom of this heatsink, but you can see the heatsink is probably where the bulk of our high temperature is. Okay. Next, what we can have a look at doing is plotting what are called isosurfaces. Now, this is one continuous surface at which the temperature is whatever value, or whatever fluid parameter we're interested in is whatever value we specify. And on that note, let's have a look at all the parameters that we can plot, because essentially once the flow solve is complete, all of the information about the fluid and the solids is available to us to go back over. So you see here we can have a look at the turbulent intensity, any of the turbulent characteristics, heat fluxes, so heat transfer rates from the solid surfaces. We can have a look at anything we like just in here. So we can in this location include these parameters in this list here for us to pick off and analyze. So here in this case I'm going to grab that fluid temperature and let's just have a look at what that's going to show us. So you see we haven't got much fluid in that particular temperature range. So I'm just going to drag that slider down a bit. And so we can see now we've got a nice fluid volume. Let's drag that up a bit again. Inside which our temperature is probably above in this case, because I know the air was a lot cooler in this region. So we've got a volume here which is encased by this surface, inside which the temperature is above 36 degrees. So that's a really nice way to find where your hot spots are and what regions you're not cooling effectively. Okay, the next tool we've got is what's called flow trajectories, and this is one of the really nice visual tools that's really good for outputting, for instance, marketing material as well as accurate results. So let's have a look at some of those. Okay, so there we go, and so now we can see what essentially we've plotted there are streamlines. So this is if we were injecting, for example, tiny particles of zero mass, this is how the fluid would carry them around the internal volume there. And what I've done is painted these trajectories with the temperature, so we can see we've got the fluid temperature coming in here at ambient, that's 20.05 degrees, so much cooler than the rest. And we've got the vast majority of the flow coming in across this side of the box. Now we've got a lot of flow trajectories visible in here, and this is around a region where it looks like the flow is probably slowed down and it's just circulating instead of going out of the enclosure. And so for that reason we can see that it's warming up quite significantly to a point where over by this heatsink we've got fluid temperature at about 64.24 degrees. So we can see majority of the flow coming in here and probably leaving rather quickly. We can also see some of the wash coming around here and circulating around the enclosure before eventually leaving as we would like. Okay, we've got a couple of other tools that we can use that we're probably going to see later on. I'll show you in the valve example instead. But we can inject particles of a mass this time, so we can conduct what's called a particle study and inject, for example, tiny iron particles or fluid like water particles, anything like that, and see how they behave within the flow. Obviously they carry a mass and hence their behavior will be different, their momentum will be different. We can also plot what are called surface parameters. This is very much like the probe tool that we had in the stress analysis tool. Instead we've got point, surface and volume parameters in here. So for example, let's grab a volume parameter and just select that heatsink again, and in this case we can output the solid temperature, hit show, and SolidWorks will work out all of the temperature characteristics of that particular solid component. And now we can see that within that volume our minimum temperature is 54.03 degrees C, our maximum temperature is 72.26 degrees, the average throughout the body is 71.42 degrees. And we can export that to Excel, and we can also grab obviously more than one body and more than one parameter to add in there. Finally, we can conduct animations and reports. So these are just ways of outputting our results. So we can generate a nice Word report with images of all our results plots and all of our study setup and the numerical outputs. And also we can grab animations and conduct videos, or create videos, sorry, of our geometry, so the flow trajectories, or we can create videos of the cut plots moving through our geometry, etc., etc. Okay, so that is in essence the very quick overview of the electronics cooling capability of SolidWorks Flow Simulation. There are additional add-ins for that, which is actually called the electronics cooling module, which gives you further capability for electronics cooling studies. So we can do dual heating, and we've got a number of additional components and capabilities within there which are very specifically tuned towards electronics cooling systems. Next, we'll have a look at a valve example. So what I've got here is a nice example of a valve. Let's just grab that section there so we can see. So we've got flow coming in through this inlet pipe, and we've got a filter through here which is going to control, depending on how high or low this arm is, how much flow is going to go in, by controlling how many of these holes the fluid can flow through. And then obviously it's going to come through here and out the outlet. So I've already conducted the study. We've already got our results just here. So let's have a look at the flow trajectories, and we can see essentially the flow. It might be easier if I stick that on a black background for the time being. How the flow is coming in a nice uniform fashion, distributing around the cap that we've got here, shooting down in through these holes into this bottom section where we've got a nice plume coming around all the way around the outside. We've got a nice vertical flow coming through and out the outlet. Let's just activate that particle study that we've got in there. And so I'll show you, in this case I've injected water particles. And so we can take advantage of the mass properties that are already in the engineering database and just have a look at how water particles would behave in this system. So we can come in and animate that and really see exactly what's going on there. As with all of the other plots and information that we've gathered out of here, we can change the values that we're painting that with. So in this case, that was painted with the flow velocity. We can change whatever value it is we want the colors to represent there, and that can give us a really nice way of analyzing not just temperature, but also flow velocity and turbulence characteristics, etc., etc., etc. So one final thing that I will show you on our valve example, and that's one of the very important characteristics of a valve system, is the pressure drop across the system. So what I've got here is a surface parameter. So I've just grabbed the external lid, so this is the outlet lid in this case. So I'm going to have a look at that surface parameter there, and you'll see SolidWorks is going to output for me the volumetric flow rate in this case. So instead, what we can do, in fact, it would help if I put the pressure on there. So let's grab the pressure as well, hit show, and SolidWorks is going to show me what the pressure at that particular location is. So in this case, our average pressure on that outlet lid is 101360. Now what we can go ahead and do is exactly the same, and I'm going to pull through where I've set up my inlet. So let's have a look at my inlet lid. Again, grab that pressure and hit show, and so we can see the average value of the pressure on the inlet, and now all we need to do is subtract the outlet from the inlet, and that gives us the pressure drop across our system. Very quick, very simple, just grabbing information from surfaces that we've already got created in our geometry. Okay, and that's about it. That's a very quick overview of SolidWorks Flow Simulation. If you're interested in demos or anything like that, then please don't hesitate to give us a call.